The sun's monster just turned to face us. Right now, as you listen to this, something extraordinary is happening 93 million miles away. A dark wound has opened on the surface of our star, and it is turning to look directly at Earth. This is not speculation. This is not sensationalism. This is happening today, December 4th, 2025, and what I am about to share with you over the next 2 hours may fundamentally change how you understand the relationship between our planet and the nuclear furnace that gives us life. The sunspot complex, designated AR 4294 through 4296, measures more than 350,000 kilometers across. To put that into perspective, you could line up 27 Earths side by side and still not span the width of this magnetic beast. It is the largest sunspot formation observed in over a decade, and it has just rotated into a position where any eruption, any release of its pent-up energy, will fire directly at our planet. But here is what makes this truly extraordinary. When astronomers compared this sunspot to historical records, they found something that sent chills through the scientific community. This formation is 90% the size of the sunspot that caused the Carrington event of 1859, the most powerful geomagnetic storm in recorded human history. And unlike 1859, we now have a global civilization utterly dependent on the very technologies that such a storm could destroy. Before we dive deeper into what is unfolding above our heads, if you find value in what you hear today, please take a moment to like this video and subscribe to the channel. This tells the algorithm that you want more content like this. Let us begin by understanding what we are actually looking at when we talk about sunspots. Most people imagine them as simple dark patches on the sun, but this dramatically undersells their true nature. A sunspot is a region where intense magnetic field lines have burst through the solar surface, creating an area so magnetically complex that it actually suppresses the convection of hot plasma from below. This is why sunspots appear darker than their surroundings. They are not actually dark at all. They are still blazingly hot, around 3,500 degrees Celsius, but compared to the 5,500 degrees surface around them, they appear as shadows. Think of it like looking at a dim light bulb next to a spotlight. The dim bulb is still producing light, but your eyes perceive it as dark by comparison. What makes AR 4294 through 4296 particularly dangerous is its magnetic classification. The National Oceanic and Atmospheric Administration has designated this region as Beta, Gamma, Delta. For those unfamiliar with this terminology, let me explain why those three words should command your attention. A beta classification means the sunspot has both positive and negative magnetic polarities. Gamma means these polarities are irregularly distributed, creating a chaotic magnetic topology. And delta, the most ominous designation, means that opposite polarity umbrae exist within a single penumbral structure. In simpler terms, imagine two enormously powerful magnets, one positive and one negative, pressed so closely together that their fields are constantly fighting, twisting, building tension like a coiled spring made of pure energy. This is the configuration most associated with the strongest solar flares, the X-class events that can reshape the near-Earth space environment in minutes. Now here is where things become genuinely fascinating, and I want you to sit with this for a moment. On December 1st, 2025, just 3 days ago, the sun erupted with an X 1.9 class solar flare. This was a powerful event by any measure, triggering radio blackouts across Australia and Southeast Asia for approximately 30 minutes. Aviation communications were disrupted, maritime signals went dark. The ionosphere, that electrically charged layer of our upper atmosphere, was suddenly flooded with enough X-ray and extreme ultraviolet radiation to fundamentally alter its behavior. But here is what the mainstream reports largely missed. That X 1.9 flare did not come from the monster sunspot we have been discussing. It came from a smaller nearby region designated AR 4299. The giant, the behemoth, the formation rivaling the Carrington sunspot, has not yet fired its main weapon. Think about that for a moment. What we experienced 3 days ago, the radio blackouts, the communication disruptions, these were caused by what amounts to a warm-up act. The headliner has not yet taken the stage. And there are troubling signs that it is preparing to do exactly that. Solar observers monitoring the region have noted significant destabilization along the southern filament of AR 4294, a filament for those unfamiliar with the term, is a massive strand of relatively cool plasma suspended in the sun's corona by magnetic field lines. When these filaments become unstable, when they snap and release their stored magnetic energy, they can trigger what scientists call sympathetic eruptions in nearby sunspots. It is like a chain of dominoes, where one falling piece triggers the next, until you have a cascade of releases that dwarf any single event. This is precisely the mechanism that concerns solar physicists right now. The December 1st flare sent a shockwave racing across the solar surface. That shockwave interacted with the unstable filament near AR4-294, and we observed the telltale signs of imminent rupture. The filament began oscillating, brightening at its anchor points, showing the characteristic signatures of magnetic reconnection beginning in earnest. If this filament releases and its trailing portion connects with the main sunspot complex, we could see an eruption orders of magnitude more powerful than what occurred 3 days ago. Let me share something that will help you understand the scale of what we might be facing. In 1859, English astronomer Richard Carrington was sketching sunspots when he witnessed something no human had ever recorded before. A brilliant white light flare erupted from the sunspot group he was observing, lasting approximately 5 minutes. What followed 17 hours later was extraordinary. Telegraph systems across Europe and North America failed catastrophically. Operators reported receiving electrical shocks. Telegraph paper caught fire spontaneously. Some systems continued operating even after being disconnected from their power sources, running on the electrical currents induced by the geomagnetic storm itself. Auroras, the northern lights, were visible as far south as Colombia and the Caribbean. People in the Rocky Mountains woke in the middle of the night, believing dawn had arrived early because the sky was so bright. Now, the sunspot that caused the Carrington event had a surface area of approximately 2,300 millionths of the solar hemisphere. The current sunspot complex measures 2080 millionths. That is 90% of the Carrington sunspot's size. But I want to be careful here because size alone does not determine the power of a solar eruption. The magnetic complexity matters enormously. The orientation of the magnetic field lines matters. The amount of stored energy and the efficiency of its release, all these factors contribute to the ultimate impact. What we can say with certainty is that AR429-4-296 possesses the magnetic complexity necessary to produce extreme flares. Whether it will do so remains an open question, but the potential is undeniably present. Here is something that mainstream coverage has largely failed to emphasize. The coronal mass ejection associated with the December 1st flare was initially projected to miss Earth entirely. The models suggested it would blast harmlessly into space, a bullet fired in the wrong direction. But those models were wrong. On December 3rd, the CME arrived at Earth, and the impact exceeded all expectations. Instead of the predicted G2 moderate geomagnetic storm, we experienced G3 strong conditions. The planetary K-index, our primary measure of geomagnetic disturbance, spiked to levels that triggered auroral displays across northern Europe and the northern United States. The storm was amplified by something called a KO, rotating interaction region, a complex knot of solar wind structures that intensified the CME's impact. Additionally, a high-speed stream from a coronal hole, a region of open magnetic field lines on the Sun, added its energy to the mix. The result was a perfect confluence of solar phenomena, each component reinforcing the others, creating a geomagnetic disturbance significantly more powerful than any single element could have produced alone. This matters enormously for our current situation. If the models underestimated a relatively modest CME from a secondary sunspot region, how confident can we be in predictions about potential eruptions from the main event? The answer, uncomfortable as it may be, is that we cannot be particularly confident at all. Solar physics has made tremendous advances over the past several decades, but our ability to predict exactly when a sunspot will erupt and how powerful that eruption will be remains frustratingly limited. We can identify dangerous configurations, we can calculate probabilities, we can issue watches and warnings, but the sun operates on its own schedule, indifferent to our models and our preparations. What we know with certainty is this: AR4294-4-296 will remain in a geo-effective position, meaning any eruption will be Earth-directed for approximately the next 7 to 10 days as it transits across the solar disk. During this window, we are essentially looking down the barrel of a loaded weapon. The The weapon may not fire. It may release its energy gradually through smaller flares and coronal mass ejections, or it may produce a single catastrophic eruption that dwarfs anything we have experienced in the modern technological era. The scientific community is watching, with a mixture of fascination and apprehension, knowing that we are witnessing something genuinely rare, something that connects us to historical events that reshaped human understanding of our relationship with the sun. But the sunspot itself is only part of the story. What happens if it does produce a Carrington-class eruption? What would that actually mean for our civilization in 2025, with our satellite constellations, our interconnected power grids, our digital infrastructure that underpins virtually every aspect of modern life? The European Space Agency recently conducted a simulation of exactly this scenario, and the results were sobering enough that they deserve their own detailed examination. The cascading failures, the timeline of impacts, the vulnerabilities we have built into our technological systems, all of these paint a picture that demands our attention. And there are signs, subtle but persistent, that the sun may be telling us something important about cycles and patterns that extend far beyond the 11-year solar maximum we learned about in school. Something is happening beneath our feet as well, deep in the core of our planet, and the timing of these events may not be coincidental at all. There is another element to this unfolding situation that requires our immediate attention, something the solar observatories captured in the hours following the December 1st flare. When the X1.9 eruption occurred, the shockwave did not simply dissipate into space. It rippled across the solar surface and interacted with a massive filament structure adjacent to the main sunspot complex. This filament, a suspended arc of plasma held aloft by competing magnetic forces, showed clear signs of destabilization. Scientists observed what they describe as oscillatory motion, combined with localized brightening, the classic precursor signatures of an imminent eruption. The filament is positioned in such a way that if it snaps, its magnetic energy will connect directly with the volatile heart of AR4294. This is the mechanism by which nearly 30% of all major solar flares are triggered, external perturbations setting off stored energy in adjacent regions. The sun, it seems, is priming itself for something significant. When filaments snap and sunspots ignite, the physics of what happens when a solar filament destabilizes is nothing short of extraordinary, and understanding this process reveals why the current situation demands such close attention. Picture, if you will, a rope made of superheated plasma, suspended hundreds of thousands of kilometers above the solar surface. This rope is not held up by any physical structure. It floats in the sun's atmosphere, the corona, balanced precariously by opposing magnetic forces. For days, weeks, sometimes months, these filaments hang in equilibrium, slowly accumulating mass as plasma condenses along their length. They grow heavier. The magnetic field lines supporting them stretch and strain. And then, without warning, the balance fails. The process typically unfolds in two distinct phases. During the first phase, the filament begins a slow rise, ascending through the corona at speeds that might seem leisurely by solar standards, perhaps 50 kilometers per second. This is the warning phase, though that warning is measured in minutes rather than hours. As the filament rises, it encounters resistance from the overlying magnetic field, the invisible cage that has kept it trapped near the solar surface. The interaction between the rising plasma and this magnetic cage triggers what physicists call magnetic reconnection, a process where opposing field lines break apart and reform in new configurations. This reconnection releases tremendous energy, heating the surrounding plasma and accelerating the filament's ascent. The second phase is where things become violent. The slow rise suddenly transforms into explosive acceleration. The filament can reach speeds exceeding 1,000 kilometers per second as it tears through the corona and erupts into space. The magnetic reconnection intensifies, releasing X-rays and extreme ultraviolet radiation in quantities sufficient to alter the ionosphere of any planet in the line of fire. If the filament is connected to a sunspot, as the one near AR4294 appears to be, its eruption can trigger a sympathetic response in the sunspot itself. The stored magnetic energy of the sunspot, pent up for days or weeks, finds a sudden pathway to release. The result is a solar flare orders of magnitude more powerful than the filament eruption alone could produce. This sympathetic triggering mechanism explains some of the most powerful solar events in recorded history. The Carrington event itself may have involved exactly this kind of cascading release, where an initial disturbance triggered a chain reaction of eruptions across multiple active regions. When we look at AR 4294 through 4296 today, we see all the ingredients for such a cascade. Multiple sunspots with complex magnetic topologies clustered together, filaments threading between them, unstable configurations that could interact and amplify each other's eruptions. The sun has assembled a powder keg, and the December 1st flare may have lit a very slow fuse. But let us talk about what actually happens when a major coronal mass ejection reaches Earth, because this is where the abstract physics becomes terrifyingly concrete. A CME is essentially a bubble of magnetized plasma, billions of tons of solar material racing through space at speeds that can exceed 3 million kilometers per hour. When this bubble collides with Earth's magnetosphere, the protective magnetic cocoon that shields our planet from the solar wind, something remarkable occurs. The magnetosphere compresses on the day side, pushed inward by the pressure of the incoming plasma. On the night side, it stretches outward, drawn into a long tail extending millions of kilometers into space. If the magnetic field carried by the CME is oriented opposite to Earth's field, a configuration called southward BZ, the two fields can merge through that same reconnection process we discussed on the Sun. This allows solar energy to pour directly into our magnetosphere, supercharging the radiation belts and driving electric currents through the upper atmosphere. These currents, in turn, induce secondary currents in any long conductor on Earth's surface. Power lines, pipelines, railway tracks, telecommunications cables. The longer the conductor, the greater the induced current. This is where modern civilization becomes vulnerable in ways that would have seemed like science fiction to Richard Carrington in 1859. Our power grids span continents, with transmission lines running thousands of kilometers from generating stations to population centers. These long conductors act as antennas, picking up the geomagnetically induced currents created by major storms. The currents flow into transformers, the massive devices that step voltage up and down throughout the grid. Under normal circumstances, transformers are designed to handle alternating current at specific frequencies. Geomagnetically induced currents are quasi-direct current, a type of electricity that transformers are fundamentally not designed to process. When these induced currents enter a transformer, they drive the iron core toward magnetic saturation. The transformer begins to heat in ways its designers never intended. Hotspots develop. Insulation degrades. In moderate storms, this causes inefficiency and premature aging. In severe storms, it causes catastrophic failure. The transformer does not merely stop working. It can literally melt, its internal components fusing into masses of copper and steel that can never be repaired, only replaced. And here is the critical problem. Large power transformers are not mass-produced items sitting in warehouses waiting to be shipped. They are custom-built devices that take 12 to 18 months to manufacture. A storm that destroys dozens or hundreds of these transformers simultaneously would create cascading blackouts, lasting not hours or days, but potentially months or years. The March 1989 geomagnetic storm offers a glimpse of this vulnerability. That event, triggered by a CME far weaker than what a Carrington-class eruption would produce, collapsed the Hydro-Quebec power grid in 90 seconds. 6 million people lost electricity for 9 hours. A transformer in New Jersey was permanently damaged. The storm caused voltage fluctuations and equipment failures across the northeastern United States and into Europe. Yet the 1989 event was perhaps 3 to 4 times weaker than the Carrington event. Scale up the impacts accordingly, and you begin to understand why governments and utilities have begun taking space weather seriously in the past decade. The European Space Agency conducted a simulation earlier this year specifically designed to test response protocols for a Carrington-class event. The scenario they modelled was sobering. Within 8 minutes of the initial flare, intense radiation disrupted radar systems, GPS signals, and high-frequency communications across the daylit hemisphere. Emergency services found themselves suddenly unable to coordinate. Aircraft in flight lost navigation capability. Ships at sea could not determine their positions. Minutes later, a storm of high-energy particles reached Earth orbit, bombarding satellites with radiation that corrupted memory, scrambled sensors, and in some cases cause permanent hardware damage. The simulation estimated that satellite drag in low Earth orbit would increase by 400% as the upper atmosphere expanded and thickened, potentially causing uncontrolled orbital decay for hundreds of spacecraft. But the true catastrophe arrived 20 hours later, when the CME itself impacted Earth's magnetosphere. The simulation showed geomagnetically induced currents exceeding 100 amperes flowing through power grid infrastructure. Transformer protective systems tripped across multiple countries simultaneously. Where protection failed, transformers overheated, and some caught fire. The interconnected nature of modern power grids meant that failures in one region cascaded into neighbouring regions as loads shifted and backup systems became overwhelmed. Within hours, the simulation showed large portions of Europe without electricity, with no clear timeline for restoration. The ESA scientists concluded their exercise with a stark assessment. A solar storm of extreme magnitude, they wrote, may cause damage to all our satellites in orbit. The immense flow of energy ejected by the Sun leaves no spacecraft safe. Even satellites in low Earth orbit, typically better protected by our atmosphere and magnetic field, would be vulnerable to an explosion of Carrington magnitude. The implications extend far beyond inconvenience. Modern society has woven satellites so deeply into its infrastructure that their simultaneous failure would blind weather forecasting, cripple financial systems that rely on precision timing, eliminate most long-distance communications, and paralyze military operations worldwide. Yet there is something almost darkly amusing about our collective response to this threat. We have known about the vulnerability for decades. Studies have outlined the risks in exacting detail. The cost of hardening the grid, installing blocking devices on critical transformers, stockpiling replacement equipment, has been estimated at perhaps $100 million for the most vulnerable 1,000 transformers in the United States. This is a rounding error in the federal budget. It is less than the cost of a single major hurricane, yet the investment has not been made, or at least not at the scale the threat warrants. Instead, we watch the sun and hope for the best. We issue forecasts and warnings, knowing that even a perfect prediction provides only hours to days of notice. We cannot stop a CME any more than we could stop an asteroid. We can only brace for impact and pray that the impact is not the big one. The sunspot complex now facing Earth represents exactly the kind of formation capable of producing that big one. Whether it will or not remains unknown. The sun keeps its own counsel, indifferent to our hopes and fears, operating on timescales and energy levels that dwarf human concerns. And here is where the story takes an unexpected turn, because the sun is not the only source of electromagnetic disruption we need to worry about. Something else has been happening, something measured not in the corona of our star but in the ionosphere above our heads and the crust beneath our feet. Signals that precede earthquakes, anomalies that appear hours or days before the ground begins to shake. Scientists have been tracking these precursors with increasing precision, and what they are finding challenges our understanding of how Earth systems interact with each other and with the space environment beyond. A storm arrives. While you sleep last night, while most of North America slept, something remarkable happened in the sky above them. The coronal mass ejection launched by the December 1st solar flare arrived at Earth approximately 48 hours after leaving the Sun, travelling at speeds approaching 700 kilometers per second. The impact with our magnetosphere occurred around 1800, universal time on December 3rd, and almost immediately, the instruments monitoring our geomagnetic environment began registering activity that exceeded all predictions. The Space Weather Prediction Center had issued a G2 moderate storm watch for December 3rd and 4th. This was a reasonable forecast based on the available data. The CME appeared to be delivering a glancing blow rather than a direct hit. The trajectory suggested the bulk of the plasma would sweep past Earth, rather than slamming directly into our magnetic field. But space weather forecasting, for all its sophistication, remains an imprecise science. The models did not fully account for what would arrive alongside the CME, a CO, rotating interaction region, a compressed boundary where fast solar wind catches up to slower wind ahead of it, reached Earth at almost precisely the same moment as the CME. Additionally, a stream of high-speed particles from a coronal hole added its energy to the mix. The combination of these three phenomena, the CME, the interaction region, and the coronal hole stream, created conditions significantly more disturbed than any single element would have produced. Instead of the predicted G2 moderate storm, Earth experienced G3 strong geomagnetic storming. The planetary K-index, our primary measure of magnetic disturbance, spiked to levels that lit up aurora forecasts across both hemispheres. From Oregon to Pennsylvania, from Washington state to New York, observers reported seeing the northern lights dancing across skies that rarely witness such displays. The aurora is, of course, simply visible evidence of invisible violence. Those shimmering curtains of green and red light are oxygen and nitrogen atoms high in the atmosphere, excited by electrons spiraling down along magnetic field lines, releasing photons as they return to their ground state. Beautiful, certainly, but also a reminder that Earth's magnetic shield is being hammered by particles carrying enough energy to penetrate deep into our protective cocoon. The storm peaked around 15:30 Eastern Standard Time on December the 3rd, reaching G3 conditions that persisted for several hours before gradually subsiding. Reports from ground stations indicated that high-frequency radio communications experienced degradation at polar latitudes. GPS accuracy suffered temporary reductions. Satellite operators reported increased drag on low Earth orbit spacecraft as the thermosphere expanded in response to the energy being dumped into it. These effects were noticeable but manageable. The grid held, the satellites survived. The storm, while impressive, remained within parameters that our infrastructure could absorb. But here is what keeps space weather forecasters awake at night. The storm that just occurred was triggered by an X1.9 flare from a secondary sunspot region, amplified by fortunate, or unfortunate depending on your perspective, timing with other solar wind, structures. The main event, the monster sunspot complex AR4-294-4-296, has not yet produced a major flare from its current Earth-facing position. It has been churning out M-class flares with regularity, 6 of them in the past 2 days alone. M-class flares are the middle tier, significant enough to cause minor radio blackouts, but typically not the stuff of headlines. They are, however, indicators of ongoing magnetic stress. Each M-class flare represents a partial release of stored energy, a small earthquake that might relieve pressure or might be a foreshock to something much larger. The question that no one can definitively answer is whether these smaller flares are bleeding off energy safely or whether they are merely preambles to a climactic eruption. Solar physicists have studied this question for decades without reaching a satisfying conclusion. Some sunspot complexes produce dozens of moderate flares and then rotate off the visible disk without ever generating an extreme event. Others sit quietly for days and then explode with minimal warning. The sun does not telegraph its intentions clearly, despite our best efforts to read the signs. What we can say is that the conditions for a major eruption exist. The magnetic topology is sufficiently complex. The stored energy is sufficiently large. The filament structure nearby shows signs of instability that could provide a trigger mechanism. Whether that trigger activates in the next few days or never activates at all remains genuinely unknown. We are watching, waiting, measuring every fluctuation in the magnetic field, every oscillation in the filament, every brightening that might herald reconnection. The sun holds all the cards, and we are merely observers trying to guess its next move. Meanwhile, something curious has been happening in the ionosphere, the electrically charged layer of our atmosphere that extends from roughly 60 to 1,000 kilometers above Earth's surface. The ionosphere is exquisitely sensitive to both solar activity and to processes occurring deep within the Earth itself. It rises and falls with the day-night cycle as solar radiation ionizes atmospheric gases. It responds to solar flares with sudden increases in electron density. But it also responds to something else, something that has puzzled scientists for decades and is only now beginning to yield to systematic investigation. Earthquakes leave signatures in the ionosphere. This is not speculation or fringe science. It is documented in peer-reviewed literature stretching back decades, though the mechanisms remain incompletely understood. The total electron content of the ionosphere, measured using GPS signals, shows anomalous variations in the days and hours before major seismic events. The critical frequency of the F2 layer, the ionospheric region most important for radio propagation, fluctuates in patterns that correlate with impending earthquakes. These are not subtle, effects visible only in retrospective analysis. They are measurable, repeatable, and increasingly predictable. A study published earlier this year examined ionospheric precursors associated with the February 2025 magnitude 7.6 Cayman Islands earthquake. The researchers found a structured hierarchy of signals appearing before the event. Acoustic gravity waves disturbed the ionosphere several hours before more obvious anomalies emerged. Regional similarity indices shifted. Ionospheric disturbance indices increased. Rate of change indicators showed turbulence developing. The sequence unfolded in predictable stages, each phase providing additional warning that something significant was building in the lithosphere below. The physical mechanism linking earthquakes to ionospheric changes is called lithosphere, atmosphere, ionosphere coupling, abbreviated LAIC. The hypothesis works like this. As tectonic stress accumulates in the crust, it creates conditions that alter the electrical properties of rocks. Piezoelectric effects in crystalline minerals generate electric fields. Radon gas, radioactive and ionizing, escapes from microfractures in stressed rock and rises through the soil. When this radon reaches the atmosphere, it ionizes air molecules near the surface, creating anomalous electrical gradients that can propagate upward into the ionosphere. But there is another pathway that researchers have identified, one involving thermal anomalies. Before some major earthquakes, satellite infrared sensors detect localized temperature increases in the region that will eventually rupture. These thermal anomalies are not large, perhaps a degree or two above background, but they are real and they are repeatable. A paper published recently re-examined historical data from a 1969 earthquake on the Iberian Peninsula and found clear thermal precursors appearing in the hours before the main shock. We have known about this phenomenon for more than 50 years, yet our earthquake warning systems remain frustratingly primitive. The connection to our current solar situation may not be immediately obvious, but consider this. The ionosphere is the medium through which both solar and seismic signals propagate. When a geomagnetic storm disturbs the ionosphere, it can mask or modify the precursor signals that might otherwise warn of impending seismic activity. Conversely, the enhanced particle precipitation during storms may actually trigger or accelerate processes already underway in the crust. The Earth is not a collection of isolated systems. It is a coupled entity where core, mantle, crust, atmosphere, and magnetosphere interact in ways we are only beginning to comprehend. And speaking of the core, there is another story unfolding deep beneath our feet that demands attention. Something has changed in the way Earth's inner core rotates relative to the mantle above it. The data is unambiguous, confirmed by multiple independent research teams using different methodologies. The solid iron heart of our planet, spinning within the liquid outer core, has altered its behavior in ways that may connect to everything we have been discussing. The timing of these changes, the relationship to geomagnetic jerks and pole shift acceleration, the correlation with surface phenomena, all of these threads may weave together into a tapestry we are only now beginning to discern. The Carrington Warning. No one wants to hear. On the morning of September 1st, 1859, Richard Carrington stood in his private observatory in Redhill, England, doing what he did most mornings. He was sketching sunspots. Carrington was an amateur in the original sense of the word, a man who pursued astronomy for love rather than profession. He had made a fortune in brewing and retired early to devote himself to the systematic observation of our star. His drawings were meticulous, his records comprehensive. He was, by the standards of his era, one of the most careful solar observers in the world. At approximately 11:18 local time, Carrington witnessed something that no human had ever consciously observed before. A brilliant white light erupted from the sunspot group he was drawing, two intensely bright patches that moved across the solar surface before fading after roughly 5 minutes. Carrington knew immediately that he had seen something significant, though he could not have understood just how significant. In his published account, he noted that the event had produced a magnetic crochet, a sudden pulse in Earth's magnetic field recorded at observatories across Europe. But he remained cautious, writing that one swallow does not make a summer, unwilling to claim a definitive connection between the solar flare and the magnetic disturbance. 17 hours after Carrington's observation, the connection became undeniable. A geomagnetic storm of unprecedented intensity struck Earth, and the world had never seen anything like it. Telegraph systems, the high technology of the Victorian era, failed across Europe and North America. Operators in Boston found they could transmit messages to Portland, Maine, with their batteries disconnected, the telegraph running on currents induced by the storm itself. telegraph paper caught fire, operators received electrical shock severe enough to knock some unconscious. The aurora borealis, normally confined to high latitudes, painted skies as far south as Colombia and Cuba. People in the Rocky Mountains woke in the middle of the night believing dawn had arrived because the sky glowed so intensely. This was the Carrington event, and it remains the benchmark against which all subsequent geomagnetic storms are measured. Scientists have estimated the flare intensity at approximately X45, though such estimates are necessarily imprecise, given the instruments available in 1859. For comparison, the largest flare of the modern satellite era was the X28 event of November 2003, and some estimates suggest even that may have been under-recorded due to detector saturation. The Carrington event was almost certainly more powerful, perhaps significantly so. Now here is the uncomfortable truth that governments and utilities have slowly begun to acknowledge over the past 2 decades. A Carrington-class event would be catastrophic for modern civilization in ways that dwarf anything in our historical experience. The 1859 storm damaged telegraph systems. A comparable storm today would damage everything. Consider what we have built since 1859. Continental power grids with transmission lines spanning thousands of kilometers. Fiber optic networks carrying the majority of global internet traffic. Satellite constellations providing navigation, communication, weather forecasting, financial timing, and military surveillance. Pipeline systems controlled by electronic sensors and actuators. Water treatment plants dependent on continuous electrical supply. Hospitals whose intensive care units, operating theatres, and life support systems require uninterrupted power. Food distribution networks that would collapse within days if trucking and refrigeration failed simultaneously. Every one of these systems contains vulnerabilities to geomagnetically induced currents, electromagnetic pulses, or the cascading failures that would follow widespread electrical grid collapse. The Lloyd's of London insurance market commissioned a study several years ago examining the risk to North America's power grid. Their analysts concluded that a Carrington-class event could affect 20 to 40 million people, with power outages lasting from 16 days to 1 to 2 years, depending on the number of transformers destroyed and the time required to manufacture replacements. The economic impact was estimated in the trillions of dollars. Total economic impact globally could reach $1.2 to $9.1 trillion over a 5-year recovery period. These numbers are so large that they become abstracted, difficult to grasp in human terms. So let us make it concrete. Imagine your city without electricity for 2 months. Not a temporary blackout measured in hours, but a sustained absence of power lasting 8 weeks or longer. No refrigeration. No water pressure in buildings taller than a few stories, since electric pumps move water through modern plumbing systems. No gasoline, since pumps at filling stations require electricity. No electronic banking, no ATMs, no credit card transactions. Grocery stores empty within days as just-in-time supply chains collapse and desperate customers strip shelves of anything edible. Now extend that scenario across multiple states or multiple countries simultaneously. Emergency services overwhelmed. Medical systems unable to function. Communications reduced to whatever can be managed by battery-powered radios and physical messengers. Civil order strained as the veneer of normalcy peels away, and the implicit contract that holds society together comes under pressure it was never designed to withstand. This is not fantasy. This is the realistic assessment of what a Carrington-class event would mean for technological civilization. And the sun has shown us repeatedly that it is capable of producing such events. The Carrington event itself occurred only 166 years ago, well within the historical record. Ice core analysis and tree ring studies have revealed evidence of even larger events in the more distant past. The Miyake event of 774 AD appears to have been perhaps an order of magnitude more powerful than Carrington, judging by the carbon-14 spike it produced in tree rings worldwide. Similar events occurred around 993 AD and at several other points in the past 10,000 years. The physics of the sun guarantees that such events will happen again. The question is not whether but when, and the answer to when is that we genuinely do not know. It could be tomorrow, it could be a century from now. The average interval between Carrington-class events appears to be roughly 100 to 200 years, which places us within the window where another could reasonably be expected. The average interval between Miyake-class events is perhaps 500 to 1,000 years, long enough that human civilization has never had to cope with one in the technological era. This brings us back to the sunspot complex currently facing Earth. AR 4294 through 4296 is not guaranteed to produce a Carrington-class event. The odds against any particular sunspot generating such an extreme eruption are substantial. But this formation represents one of the more concerning configurations we've seen in the current solar cycle. Its size, its magnetic complexity, its position facing directly at Earth, all these factors combine to elevate the risk above the normal background level. For the next week, as this region transits the solar disk, we are in a period of elevated vulnerability. The sensible response to this situation is the same sensible response that has been recommended for decades: harden the grid. Install blocking devices on critical transformers, stockpile replacement equipment, develop protocols for rapid grid disconnection if warning time permits, invest in space weather forecasting to maximize that warning time. These measures are not exotic or impossibly expensive. They are engineering solutions to an engineering problem, and they could dramatically reduce the impact of even a severe event. Yet progress has been frustratingly slow. Utilities resist unfunded mandates. Regulators balance grid reliability against rate increases. Politicians find it difficult to prioritize threats that may not materialize during their terms in office. The result is a gradual, incremental improvement in preparedness that may or may not prove adequate when the next major storm arrives. We are playing a slow-motion game of chicken with the sun, betting that the big one will not arrive before we get around to proper preparation. Meanwhile, the sun continues its cycles, indifferent to human schedules and priorities. Solar cycle 25, the current cycle, appears to have peaked or to be peaking now, in late 2024 and into 2025. The sunspot numbers, the flare frequencies, the general level of activity all suggest we are at or near solar maximum. This is precisely when the risk of extreme events is highest. The next few years represent a window of elevated vulnerability, a period when the statistical likelihood of a Carrington-class event is somewhat higher than average. None of this means we should panic. Panic serves no purpose and clouds judgment. But awareness matters. Understanding the nature of the threat matters. Recognizing that our technological civilization rests on foundations more fragile than most people realize, this awareness can motivate the kind of prudent preparation that might make the difference between inconvenience and catastrophe when the sun finally reminds us who is really in charge. The warning signs are there for anyone willing to read them. The massive sunspot facing Earth, the filament poised to snap, the storm that exceeded predictions just last night. These are not random events. They are manifestations of processes that will eventually produce something we're not prepared to handle. The only question is whether that something arrives before or after we have done the work necessary to survive it. And perhaps, just perhaps, the warning signs extend beyond the sun itself. There are researchers who believe that what happens in the solar system, what happens in Earth's magnetosphere, and what happens deep in Earth's interior are connected in ways our models have not yet captured. The next thread of our story takes us down, far down, into the slowly churning iron heart of our planet, where something has changed in ways that may have consequences none of us anticipated. The Earth whispers before it screams. There is a pattern that appears in the data if you know where to look. In the hours and days before major earthquakes, anomalies ripple through the ionosphere like whispers of what is to come. Total electron content shifts in ways that cannot be explained by solar activity alone. The critical frequency of the F2 layer fluctuates. Acoustic gravity waves propagate upward from regions that will soon experience catastrophic rupture. The Earth, it seems, does not suffer in silence. It signals its distress through channels we're only beginning to learn how to monitor. The science of earthquake precursors has a troubled history. For decades, claims of prediction methods were met with skepticism, bordering on hostility from the seismological establishment. Too many false alarms, too many failed predictions, too many researchers whose enthusiasm outpaced their evidence. The field earned a reputation for attracting charlatans and wishful thinkers. Serious scientists learned to avoid it if they valued their careers. But the data kept accumulating. Satellite after satellite recorded ionospheric anomalies coinciding with major seismic events. The Demeter mission, a French spacecraft specifically designed to study earthquake, ionosphere coupling, gathered years of observations showing clear correlations between crustal stress and upper atmospheric disturbances. The more carefully researchers looked, the more evident it became that something real was happening, even if the mechanisms remained poorly understood. The lithosphere, atmosphere, ionosphere coupling model has emerged as the leading explanation. The Leck hypothesis proposes that as tectonic stress accumulates in fault zones, it triggers a cascade of effects that propagate upward through the atmosphere and into the ionosphere. The process begins deep in the crust, where rocks under extreme pressure undergo changes in their electrical properties. Crystalline minerals exhibit piezoelectric effects, generating electric fields in response to mechanical stress. Microfractures open in the rock, allowing trapped gases to escape. Radon is particularly significant among these escaping gases. This radioactive element is produced by the decay of uranium and thorium in crustal rocks. Normally, radon remains trapped in soil and bedrock, posing a health hazard primarily in poorly ventilated basements. But when stress fractures rock, radon can migrate upward through newly opened pathways. When it reaches the atmosphere, its radioactive decay ionizes air molecules, creating anomalous electrical conditions at the surface. These electrical anomalies do not remain at the surface. The global electric circuit, the continuous flow of current between the ionosphere and Earth's surface, provides a pathway for disturbances to propagate upward. Changes in surface electrical conditions modify the current flow, which in turn affects the ionosphere. Additionally, the release of trapped gases can trigger thermal anomalies as chemical reactions occur. These thermal changes alter atmospheric density, launching acoustic gravity waves that travel upward and disturb the ionosphere through purely mechanical means. The result is a multi-channel warning system that the Earth activates before major earthquakes. Researchers studying the February 2025 Cayman Islands earthquake found a structured sequence of precursors. Acoustic gravity wave disturbances appeared several hours before the main shock, representing the earliest detectable signal. These were followed by shifts in regional similarity indices, mathematical measures of how similar the ionospheric conditions in one location are to conditions in nearby locations. Anomalous dissimilarity indicated that something was perturbing the ionosphere in a localized manner. Next came increases in the ionospheric disturbance index, a measure of how much total electron content deviates from expected values. Finally, rate of change indicators showed turbulence developing, with electron content fluctuating more rapidly than normal. The entire sequence unfolded over a period of hours, providing what could theoretically serve as a warning window if the signals could be interpreted in real time. Similar patterns have been documented for earthquakes around the world. The 2024 Noto Peninsula earthquake in Japan showed synchronized anomalies in land surface temperature, total electron content, and electron density approximately a week before the magnitude 7.1 event. The 2023 Jishishan earthquake in China produced high-frequency ionospheric perturbations, consistent with acoustic gravity wave signatures. Again and again, the pattern emerges. The crust communicates its distress through atmospheric and ionospheric channels that we are learning to read. But here is where the story becomes more complex and more intriguing. The ionosphere is not only sensitive to processes in the lithosphere, it is simultaneously responding to processes in the magnetosphere, which is driven by solar activity. When a geomagnetic storm disturbs the ionosphere, it creates noise that can mask the subtle signals of earthquake precursors. Conversely, some researchers have proposed that geomagnetic disturbances might actually trigger earthquakes, providing the final push that releases accumulated tectonic stress. The evidence for solar seismic coupling is more controversial than the evidence for ionospheric precursors, but it is not dismissible. Statistical studies have found correlations between periods of high solar activity and earthquake frequency in some regions. The physical mechanism would involve induced currents flowing through the crust, modifying fluid pressures in fault zones, or altering the electrical properties of rocks in ways that affect friction. None of these mechanisms has been definitively proven, but neither have they been ruled out. What is clear is that Earth systems are more interconnected than our compartmentalized scientific disciplines have historically recognized. The Sun affects the magnetosphere, which affects the ionosphere, which is also affected by the lithosphere, which may in turn be influenced by the Sun through pathways we do not fully understand. Drawing neat boundaries around these systems and studying them in isolation may have caused us to miss relationships that only become apparent when we examine the whole. there is another channel through which the Earth whispers before it screams, one that was largely dismissed until relatively recently. Thermal anomalies, localized temperature increases detected by satellite infrared sensors, appear over regions that will subsequently experience major earthquakes. A recent paper re-examined data from a 1969 earthquake on the Iberian Peninsula and found clear thermal precursors that had begun hours before the main shock. The researchers were looking back at historical data with modern analytical techniques, but the principle is the same. Heat escaping from stressed rock provides a signal that can potentially be detected from space. The thermal signal likely results from multiple mechanisms. Friction along fault surfaces generates heat as rocks grind past each other during the slow slip that precedes rupture. Chemical reactions involving fluids migrating through newly fractured rock can be exothermic. Piezoelectric currents flowing through resistive rock dissipate energy as heat. Whatever the source, the result is a measurable temperature anomaly that can persist for hours or days before the earthquake occurs. Combining thermal monitoring with ionospheric monitoring could potentially provide a more robust warning system than either approach alone. Different precursor types appear at different times before an event, creating a timeline that could theoretically allow for graduated alerts as confidence in an impending earthquake increases. Acoustic gravity waves might provide the earliest signal, followed by thermal anomalies, followed by total electron content shifts, followed by the immediate precursors that appear in the final hours. None of this constitutes reliable earthquake prediction in the operational sense. We cannot currently tell you that a magnitude 7 earthquake will strike a specific location at a specific time with enough precision to enable evacuation or emergency preparation. The signals are statistical, probabilistic, subject to false alarms and missed events, but the direction of research is clear. We are learning to listen to the Earth's whispers, even if we cannot yet interpret them with the precision we would like. The current situation, with major geomagnetic disturbances occurring while we monitor ionospheric conditions, provides an opportunity and a challenge. The G3 storm that struck last night created significant ionospheric perturbation. If any earthquake precursors were developing in the same time frame, they might have been obscured by the solar, induced noise. Alternatively, the magnetic disturbance might have provided a stress input to any faults already near critical states. We are watching, measuring, analysing. The instruments do not care about our schedules or our preferences. They record what they record, and we struggle to interpret the signals. Somewhere deep in the crust, stresses are accumulating that will eventually release in earthquakes. Somewhere in the ionosphere, those stresses may already be broadcasting their presence to anyone equipped to listen. And somewhere even deeper, in the iron core of our planet, something else is happening, something that may connect to both the solar activity above and the seismic activity within. The Earth is not a static ball of rock orbiting a distant star. It is a dynamic system, constantly exchanging energy with its environment, constantly evolving in response to forces internal and external. The inner core spins differently than the mantle. The magnetic poles wander. The field itself fluctuates in ways that may presage more dramatic changes to come. These processes unfold on timescales that dwarf human lifespans, yet their effects ripple into our daily lives in ways we rarely appreciate. Let us descend now in our imagination, through the crust and into the mantle, through the liquid outer core with its churning convection cells, generating the magnetic field that protects us from cosmic radiation, down to the solid iron heart at the center of everything. Something is happening there, something that scientists have only recently confirmed, something that may matter more than we ever imagined. Something moved deep below our feet, 5,000 kilometers beneath your feet. A solid iron sphere the size of the moon spins within a sea of liquid metal. This is Earth's inner core, the densest part of our planet, formed from iron and nickel that sank to the center billions of years ago and crystallized under pressures so extreme that the metal remains solid despite temperatures exceeding 5,000 degrees Celsius. For most of the history of geophysics, scientists assumed this inner core rotated in lockstep with the rest of the planet. It was, after all, gravitationally coupled to the mantle above. Why would it spin at any different rate? Then, in 1996, researchers noticed something strange. Seismic waves from earthquakes were taking slightly different amounts of time to travel through the inner core compared to previous decades. The most logical explanation was that the inner core was rotating at a different speed than the mantle and crust, causing the crystal structure of the iron to present different faces to seismic waves over time. The inner core, it seemed, was super-rotating, spinning slightly faster than the rest of the planet. This discovery sparked decades of research and considerable controversy. Different teams analysing different datasets reached different conclusions about the rate and even the direction of differential rotation. Some found superrotation, others found subrotation. Some found evidence of periodic changes in rotation rate. The inner core, invisible to direct observation and accessible only through the indirect evidence of seismic waves, refused to reveal its secrets easily. What has emerged from this research is a picture far more dynamic than anyone anticipated. The inner core does not simply spin at a constant rate relative to the mantle, it oscillates. A study published in Science Advances demonstrated that between 1969 and 1971, the inner core was subrotating, spinning slightly slower than the mantle. Then, between 1971 and 1974, it reversed direction and began superrotating. The data came from analysis of seismic waves generated by nuclear tests, which provided precisely located and precisely timed sources that allowed researchers to detect subtle changes in wave travel times. The oscillation appears to have a period of approximately 6 years, with the inner core swinging back and forth like a pendulum, first accelerating ahead of the mantle and then falling behind. But there is also evidence for longer period variations. Research from Peking University suggested that the inner core may oscillate on a roughly 70-year cycle, switching direction approximately every 35 years. Other studies have found evidence for an 8.5-year wobble, a periodic tilting of the inner core axis relative to the mantle. What drives these oscillations? The leading hypothesis involves gravitational coupling between the inner core and the mantle. Both the inner core and the mantle contain density variations, regions that are slightly denser or less dense than their surroundings. These density variations create gravitational attractions that tend to lock the inner core and mantle into alignment. But the inner core is also coupled to the outer core through electromagnetic forces generated by the geodynamo, the convection of liquid iron that produces Earth's magnetic field. When these two coupling mechanisms conflict, the inner core can oscillate around an equilibrium position, pulled one way by gravity and another by electromagnetic forces. The implications extend beyond abstract geophysics. Inner core oscillation appears to correlate with measurable changes at Earth's surface. The length of day, the time it takes Earth to complete one rotation, varies by milliseconds in ways that track the 6-year inner core cycle. When the inner core superrotates, angular momentum is transferred away from the mantle, and the mantle slows slightly, lengthening the day. When the inner core subrotates, the opposite occurs. These are tiny changes measured in fractions of a millisecond, but they are real, and they are measurable. More intriguingly, inner core oscillation may connect to variations in Earth's magnetic field. The geodynamo operates in the outer core, but the inner core provides a boundary condition that affects how the dynamo functions. Changes in the inner core rotation could modify the flow patterns in the outer core, which would in turn affect the magnetic field generated by those flows. Some researchers have proposed that certain features of geomagnetic secular variation, the slow changes in the field that occur over years and decades, might be explained by inner core dynamics. And then there is the question of whether the inner core's behavior is purely internal or whether it responds to external influences. The sun, through the solar wind and geomagnetic storms, deposits energy into the magnetosphere and ionosphere. Some of this energy couples into the solid Earth through induced currents flowing in, the crust and mantle. Could solar activity influence the inner core? The question sounds far-fetched, but the connections between systems that we once thought were isolated keep surprising us. There is another dimension to inner core dynamics that has emerged from recent research. The inner core is not merely rotating, it may be changing shape. A study published in late 2024 found evidence that the surface of the inner core is deforming over time. Patches may be rising or subsiding by hundreds of meters per decade, driven either by gravitational interactions with the mantle or by material flow in the outer core. The inner core, far from being a static and unchanging iron ball, is a dynamic object whose properties evolve on timescales that are short by geological standards. This brings us to a discovery that has captured scientific attention and raised questions we are still struggling to answer. multiple independent research teams have now confirmed that the inner core appears to have slowed its rotation significantly in recent years. Some analyses suggest it may have essentially stopped its differential rotation around 2023. Others suggest it has actually reversed, now subrotating relative to the mantle after decades of superrotation. If this is correct, we are living through a transition point in the inner core's oscillation cycle. The last such reversal, if the 70-year periodicity holds, would have occurred around 1950, which is consistent with some paleomagnetic evidence. The next reversal would not occur until late in this century, but shorter period oscillations are superimposed on this longer cycle, creating a complex pattern of variation that we are only beginning to disentangle. What does this mean for those of us living on Earth's surface? In the short term, probably not much that we would directly notice. The changes in day length are too small to detect without atomic clocks. The changes in the magnetic field unfold too slowly to affect our daily lives. But over longer timescales, inner core dynamics may matter profoundly. If the inner core influences the geodynamo, and if the geodynamo controls the magnetic field, then understanding inner core oscillation becomes essential for predicting how the field will evolve in the coming decades and centuries. And the magnetic field, as we have discussed, is what protects us from the solar wind, from cosmic radiation, from the charged particles that would otherwise strip away our atmosphere and irradiate our planet's surface. A weakening field, a reversal, a dramatic pole shift. Any of these could have consequences for both technology and biology. We do not know exactly how vulnerable we are because the modern human has never experienced such a transition. The last full reversal was 780,000 years ago, long before civilization existed. But there are signs that the field is behaving unusually. The North Magnetic Pole has been accelerating, moving from its historical position in Arctic Canada towards Siberia at speeds that have increased dramatically over the past few decades. A zone of weakness called the South Atlantic Anomaly has been expanding, a region where the field is so weak that satellites experience elevated radiation exposure when passing through it. These changes may be normal fluctuations, or they may be harbingers of something more significant. The timing of these observations creates an interesting pattern when we look at it alongside other data. The inner core appears to have undergone significant changes in its behavior during the mid-2000s, roughly coinciding with a well-documented geomagnetic jerk, a sudden acceleration in the rate of change of the magnetic field. That period also coincides with an acceleration in the drift of the North Magnetic Pole. Are these phenomena connected? Some researchers believe they are, that what happens in the inner core propagates outward through the outer core, and eventually manifests in magnetic field behavior detectable at the surface. If this is correct, then monitoring the inner core through seismic techniques might provide early warning of magnetic field changes that could affect everything from navigation to technology to climate. The Earth beneath us is not solid ground in the sense we usually imagine. It is a dynamic, evolving system where the deepest layers influence the surface, and the surface may even influence the depths. We stand on the thin skin of a machine we barely understand, conducting experiments in planetary engineering through our emissions and our magnetism and our nuclear tests, while the core rotates and wobbles and perhaps responds in ways we have not yet learned to predict. There is one more piece of this puzzle that demands attention, one that brings together the inner core dynamics, the magnetic field changes, and the broader question of how our planet is responding to forces both internal and external. It is a phenomenon called a geomagnetic jerk, and when we examine when these jerks have occurred and what followed them, a disturbing pattern begins to emerge, the jerk that changed everything. In geophysics, the word jerk has a specific technical meaning borrowed from classical mechanics. Jerk is the rate of change of acceleration, the third derivative of position with respect to time. When we speak of geomagnetic jerks, we mean sudden changes in the second derivative of Earth's magnetic field, moments when the field's rate of change itself changes abruptly. These events typically unfold over periods of 1 to 2 years and are detectable at magnetic observatories worldwide. The first systematically documented geomagnetic jerk occurred in 1969. Others have been identified in 1978, 1991, 1999, 2003, 2007, and 2011. Some events appear global, detected at observatories, across all continents. Others are more regional, affecting primarily one hemisphere or one sector of the globe. The 1969 jerk, for example, was one of the clearest global events ever recorded, observed virtually everywhere magnetometers were operating. What causes these sudden accelerations in the field? The short answer is that we do not entirely know. The magnetic field is generated by convective motion in the liquid outer core, the churning of electrically conducting iron that produces electric currents and thereby magnetic fields. Changes in this convection should manifest as changes in the observable field at Earth's surface, but the mantle that lies between the outer core and the surface is also electrically conducting, and it filters out rapid variations. Changes faster than about 1 year are strongly attenuated, which is why we cannot observe day-to-day fluctuations in core processes. Geomagnetic jerks represent changes that occur on timescales just long enough to penetrate this mantle filter. They appear to originate from sudden reorganizations of flow patterns near the core, mantle boundary. Some researchers have proposed that jerks result from the arrival of Alvan waves at the core surface, hydromagnetic waves that propagate through the liquid core and focus their energy at specific locations. Others suggest that jerks reflect torsional oscillations, patterns of differential rotation between cylindrical shells of fluid in the outer core. Whatever their ultimate cause, geomagnetic jerks are real phenomena with measurable consequences. They mark transitions in the secular variation of the field, the slow changes in field strength and direction that occur over years and decades. Before a jerk, the field changes at one rate. After the jerk, it changes at a different rate. The accumulated effect of these transitions shapes the long-term evolution of Earth's magnetic field. Now here is where the story becomes particularly interesting. The timing of geomagnetic jerks appears to correlate with changes in other Earth system parameters. Length of day variations show connections to jerk timing, suggesting that angular momentum exchange between the core and mantle may be involved. Some researchers have found correlations between jerks and irregularities in Earth's rotation, moments when the pole wobbles in unexpected ways, or when the length of day deviates from predicted values. The period from 2005 to 2008 saw particularly significant activity. Analysis of data from the CHAMP satellite, a German spacecraft designed to measure Earth's magnetic field with unprecedented precision, revealed that the secular acceleration of the field underwent two distinct power pulses during this period, one in 2006 and another in 2009. These pulses were concentrated in specific regions of the core, mantle boundary, primarily in the low-latitude Atlantic sector and the Indian Ocean sector. The pulses marked the beginning and ending of an interval of intense magnetic change that left a lasting imprint on field behavior. This same period coincides with a dramatic acceleration in the drift of the North Magnetic Pole. For centuries, the North Magnetic Pole had wandered slowly, moving at most a few kilometers per year. It had been located in Arctic Canada since continuous measurements began in the 19th century. But starting around 1990 and accelerating through the 2000s, the pole began moving faster and faster. By 2005, it was racing towards Siberia at more than 50 kilometers per year, a speed that forced navigation authorities to update their magnetic declination charts more frequently than ever before. The cause of this acceleration appears to be a reorganization of magnetic flux at the core, mantle boundary beneath Canada. A lobe of negative magnetic flux, essentially an intense patch of magnetic field pointing into the core, had long anchored the North Magnetic Pole in its Canadian position. But between 1970 and 1999, this lobe elongated and weakened, possibly due to changes in the pattern of fluid flow in the outer core. The weakening of the Canadian lobe allowed a competing lobe beneath Siberia to exert more influence on the pole position, pulling it eastward across the Arctic Ocean. By late 2017, the North Magnetic Pole crossed the international dateline, passing within 400 kilometers of the geographic pole. It continues to move southward into Siberia, though the rate of motion may now be slowing. The World Magnetic Model, the standard reference used for navigation, required an unprecedented out-of-cycle update in 2019 because the pole was moving so quickly that the model became inaccurate before its scheduled update date. These changes in pole position and magnetic field behavior are not isolated phenomena. They connect to deeper processes within the planet. The geomagnetic jerks, the pole acceleration, the inner core oscillation, the secular variation pulses, all of these may be different manifestations of the same underlying dynamics. The outer core is reorganizing its flow patterns, the inner core is changing its rotation, The field generated by these processes is evolving in response. We are watching a planetary scale adjustment unfold in real time. But here is where speculation begins, and I want to be clear about where observation ends and hypothesis begins. The period from 2005 to 2008 marked not only a geomagnetic event, but also something of a societal inflection point. The world that existed before 2008 feels qualitatively different from the world that emerged afterward. The financial crisis, the acceleration of political polarization, the erosion of institutional trust, the rise of social media-driven information warfare, the strange unreality that seems to pervade public discourse. Is there a connection between geomagnetic changes and human behavior? This idea sounds immediately suspect, the kind of claim that belongs in conspiracy forums rather than scientific discussions. Yet the question is not entirely without foundation. Human physiology includes numerous systems sensitive to magnetic fields. The pineal gland, which regulates circadian rhythms, contains magnetite crystals. Some researchers have proposed that these crystals respond to geomagnetic fluctuations, potentially affecting melatonin production and sleep patterns. Studies have found correlations between geomagnetic activity and hospital admissions for cardiovascular events, psychiatric episodes, and suicides. The effects are small and the mechanisms uncertain, but the correlations keep appearing in data from different countries and different time periods. If geomagnetic fluctuations do affect human cognition and emotion, even subtly, then a period of unusual magnetic activity might manifest as a period of unusual collective behavior. I want to be cautious here. Correlation does not imply causation. The factors that produce the social and political transformations of the past 15 years are complex and multiply-determined. Economic inequality, technological change, demographic shifts, the legacy of policy decisions, all these played roles that do not require invoking geomagnetic influences. The claim that magnetic field changes caused Clown World, as some have put it, requires a level of evidence that does not currently exist. And yet, the timing is suggestive. The mechanisms are not impossible. The sheer strangeness of recent history invites unusual explanations. When everything seems to have gone off the rails simultaneously, when rationality appears to have fled public life, when institutions that functioned for decades suddenly seem paralyzed, one naturally wonders if something fundamental has shifted. What we can say with confidence is that something happened in the mid-2000s at the planetary level. The inner core changed its behavior, the magnetic pole accelerated, geomagnetic jerks restructured the secular variation. These changes were real, measurable, documented in scientific literature. Whether they connect to anything else remains an open question, one that may never be definitively answered. The more immediate relevance of geomagnetic history lies in what it tells us about the future. The field has been weakening for the past few centuries. The South Atlantic anomaly has been expanding. The North Magnetic Pole has been racing toward a new equilibrium position. Some researchers have speculated that we may be approaching a geomagnetic excursion, a temporary reduction in field strength that stops short of a full reversal. Others wonder whether a full reversal might be beginning, a process that would unfold over thousands of years, but could begin with the kind of changes we're already observing. A weakened magnetic field would mean increased exposure to solar radiation, particularly during major geomagnetic storms. The very CMEs and flares we have been discussing would have greater impact on an Earth whose protective shield had diminished. Satellites would experience more radiation damage, astronauts would face higher risks, the ionosphere would be more easily disturbed, the interconnected infrastructure we depend upon would become more vulnerable. This is why understanding what is happening in the core matters for understanding what is happening at the surface. The sunspot facing Earth and the oscillating inner core are not separate stories. They are part of the same story, the story of a planet embedded in a solar system, subject to forces external and internal, navigating a universe that cares nothing for human convenience. And speaking of external forces and inconvenient realities, there is another thread of our story that we have not yet fully explored. The extreme cold gripping the United States right now, the Arctic blast setting record low temperatures, the polar vortex instability that has sent frigid air southward to latitudes that rarely experience such extremes. What is happening in our atmosphere, and how does it connect to everything else we have been discussing? When the pole accelerated and the world went mad, We have been speaking of geomagnetic jerks and inner core oscillations as if they were abstract scientific curiosities, interesting to specialists but distant from daily life. Let us now consider how these phenomena might manifest in ways that affect ordinary people. The story I am about to tell is speculative in parts, but it is grounded in documented changes that researchers have measured and published in peer-reviewed journals. Between 1990 and 2005, the North Magnetic Pole accelerated from its historical speed of 0 to 15 kilometers per year to a new speed of 50 to 60 kilometers per year. This is not a subtle change. It represents an increase of roughly 400% in the rate at which our planet's magnetic pole is moving. The acceleration required updating navigational charts, adjusting airport runway designations, and recalibrating countless systems that depend on accurate magnetic declination data. But the magnetic pole does not move in isolation. Its position is determined by the configuration of magnetic field lines emerging from the core, which in turn reflects the pattern of fluid flow in the outer core, which is gravitationally and electromagnetically coupled to the inner core. When the pole accelerates, something has changed in the deep Earth. The question is, what else might change as a consequence? The South Magnetic Pole has shown different behavior. While the North Pole has raced towards Siberia, the South Pole has moved more slowly, its drift rate actually decreasing over the same period. The asymmetry suggests that whatever is happening in the core is not a simple, uniform reorganization, but a complex restructuring that affects different regions in different ways. The dipole moment of the field, a measure of its overall strength, has been declining at a rate of roughly 5% per century for the past few hundred years. This decline appears to be accelerating. Some researchers have proposed that these changes represent the early stages of a geomagnetic reversal, the kind of pole flip that has occurred hundreds of times in Earth's history. During a reversal, the North and South magnetic poles essentially swap positions, a process that unfolds over thousands of years and involves a period of significantly weakened and chaotic field behavior. The last full reversal occurred roughly 780,000 years ago. On geological timescales, we are overdue for another, but others point out that reversals are preceded by excursions, temporary weakening events that look like the beginning of a reversal but ultimately recover without the poles fully swapping. The Lachamp event, about 41,000 years ago, was such an excursion. The field weakened dramatically, the poles wandered erratically, and then the system stabilized back to its previous configuration. Whether we are seeing the early signs of an excursion, a reversal, or simply normal variation within a stable field remains genuinely uncertain. What we can say is that the field is doing something unusual by historical standards. The acceleration of pole movement, the expansion of the South Atlantic anomaly, the declining dipole moment, the geomagnetic jerks of the past few decades, these phenomena collectively suggest a magnetic field in transition. Where that transition leads is unknown. Now consider the implications if the transition includes a period of significantly weakened field strength. The magnetosphere, our protective bubble, would shrink. The boundary between the solar wind and Earth's domain would move closer to the planet. Particles that currently deflected safely around us would penetrate deeper into the atmosphere. Cosmic rays from beyond the solar system would reach the surface in greater numbers. The biological effects of increased radiation exposure are well documented. Cancer rates would rise. DNA damage would accumulate. Organisms that depend on magnetic field sensing for navigation, including birds, sea turtles, whales, and many insects, would experience disruption to their orientation systems. The ionosphere, more directly exposed to solar radiation, would become more variable and more easily disturbed. But there is another effect that rarely gets discussed, one that ventures into territory where speculation outweighs evidence. The magnetic field may interact with consciousness in ways we do not understand. Every electrical system generates a magnetic field. The human brain is an electrical system, running on the tiny currents that flow between neurons. The magnetic fields generated by neural activity are extraordinarily weak, measured in femtoteslas, but they are real and they can be detected by sensitive instruments. The global geomagnetic field is millions of times stronger than the magnetic fields produced by human brains. It forms a background against which neural activity unfolds. What happens to cognition when that background changes? We do not know. The experiments required to answer such questions definitively have never been conducted. but studies showing correlations between geomagnetic activity and human behavior suggest that the interaction, whatever its nature, is not negligible. Consider the timing once more. The mid-2000s saw not only geomagnetic changes, but also the rise of social media, the financial crisis, the beginning of the political polarization that has since intensified into tribal warfare. The smartphone was introduced in 2007. Twitter had launched in 2006. Facebook opened to the general public in 2006. The infrastructure for a new kind of collective consciousness was being built at precisely the moment when the magnetic environment was undergoing unusual changes. Is this coincidence? Almost certainly. The social and technological developments of that period have sufficient causes that do not require invoking geomagnetic influences. The attention economy, the algorithmic amplification of outrage, the business models that profit from engagement regardless of its quality, these explain much of what followed. We do not need to invoke magnetic field effects to understand why people argue on the internet. And yet there is something about the collective mood that feels different from what came before. An edginess, an irrationality, a disconnection from shared reality that seems to have intensified precisely as the magnetic pole began its race across the Arctic. The institutions that once commanded respect are now viewed with suspicion across the political spectrum. The experts that once guided public discourse are now dismissed as partisan actors. The very concept of objective truth seems to have become contested. Perhaps this is simply what happens when a civilization encounters technology that exceeds its wisdom. Perhaps it is the inevitable result of economic systems that concentrate wealth while atomizing communities. Perhaps it is the natural evolution of a species whose tribal psychology was shaped by small groups and is now overwhelmed by a global information environment. These explanations make sense. They are sufficient. They do not require magnetic fields. But the question remains open, a gap in our understanding that may never be filled. Something changed in the deep earth during the mid-2000s. Something changed in human societies during the same period. Whether these changes are connected, we do not know. Whether we could detect such a connection if it existed, we are not sure. The tools for studying the interaction between geomagnetic phenomena and collective human behavior barely exist. What we can do is observe. We can note that the North Magnetic Pole continues its journey towards Siberia. We can measure the continuing decline in dipole moment. We can track the expansion of the South Atlantic anomaly, and we can watch human societies to see whether the patterns of recent years continue, intensify, or eventually subside as new equilibria are reached. The story we are telling tonight encompasses the sun and its sunspots, the magnetic field and its wandering poles, the inner core and its oscillations, the ionosphere and its earthquake precursors. All of these threads weave together into a tapestry of interconnected systems that we are only beginning to understand. The planet we live on is not a simple stage on which human dramas play out. It is a dynamic participant in those dramas, affecting us in ways we perceive dimly, if at all. And right now, at this moment, that planet is experiencing something unusual on multiple fronts. A massive sunspot stares at us from the face of the sun. A geomagnetic storm has just washed over us stronger than predicted. The magnetic pole continues its unprecedented journey. The inner core has apparently slowed or reversed its differential rotation, and across the northern hemisphere, an Arctic blast is driving temperatures to record lows, reminding us that climate is not merely a matter of long-term averages, but of extremes that can arrive with devastating suddenness. That Arctic blast deserves our attention. What is happening in our atmosphere right now, and how does it connect to the larger story we have been exploring? The cold that shouldn't be here. As I record these words, more than 220 million Americans are experiencing below-average temperatures. Schools have closed across multiple states. Record lows are falling from the Midwest to the Mid-Atlantic. Temperatures in some regions are running 15 to 25 degrees below normal, more typical of early February than early December. The polar vortex, that great wheel of cold air normally spinning above the Arctic, has fractured, sending tentacles of frigid air southward into latitudes that rarely experience such extremes. This is not a gentle cold snap. This is an atmospheric event that has sent the National Weather Service scrambling to issue warnings across more than 15 states. More than 40 record low temperatures are possible over the coming days. The heart of the cold is expanding from the Midwest toward the Interstate 95 corridor, bringing conditions that will stress heating systems, endanger vulnerable populations, and remind everyone that we remain at the mercy of forces far larger than ourselves. The immediate cause is clear enough. A phenomenon called sudden stratospheric warming has disrupted the polar vortex. High in the atmosphere, roughly 30 to 50 kilometers above the Arctic, temperatures have spiked dramatically, weakening the winds that normally keep cold air bottled up near the pole. When those winds weaken, the cold air escapes southward, bringing Arctic conditions to regions unaccustomed to them. Sudden stratospheric warming events are not rare. They occur on average about once every other winter, but their effects vary considerably depending on the strength of the warming and the larger atmospheric patterns in which they occur. This year's event appears to be significant, producing effects that will likely persist through much of December and potentially into January. Forecasters are predicting that the cold start to winter will extend well beyond the current Arctic blast. But here is where the story becomes more complex. The polar vortex is not an isolated system. It interacts with patterns throughout the atmosphere and, increasingly, with conditions we would not normally associate with weather. The vortex is fundamentally a thermal phenomenon, driven by the temperature difference between the polar regions and the mid-latitudes. When that temperature difference is strong, the vortex is strong. When it weakens, the vortex becomes unstable and prone to disruption. Climate change is altering the temperature distribution of the planet in complex ways. The Arctic has been warming faster than lower latitudes, a phenomenon called Arctic amplification. This reduces the temperature gradient between pole and mid-latitudes, which should theoretically weaken the polar vortex and make disruptions more likely. Some researchers believe we are seeing exactly this effect, that the polar vortex instabilities of recent years are connected to the changing Arctic. Others dispute this interpretation, pointing out that natural variability in the vortex has always been substantial, and that attributing specific events to climate change is methodologically difficult. The debate continues in the scientific literature, with strong opinions on both sides. What is clear is that polar vortex disruptions have been occurring with notable frequency in recent winters, bringing extreme cold to regions that had become accustomed to milder conditions. The current event is particularly significant because it coincides with so much else. We have a major sunspot facing Earth. We have just experienced a G3 geomagnetic storm. The magnetic pole continues its accelerated drift. The inner core appears to be in a transition phase, and now the atmosphere is delivering an extreme cold event that will affect hundreds of millions of people. The systems of our planet are all doing something noteworthy simultaneously. Is there a connection? The honest answer is that we do not know. Some researchers have proposed links between solar activity and weather patterns, suggesting that variations in solar output can influence jet stream behavior and thereby affect surface weather. The mechanisms are disputed, but the correlations keep appearing in data analyses. Other researchers have proposed that geomagnetic activity affects atmospheric chemistry, particularly ozone levels in the stratosphere, which could in turn influence polar vortex stability. These ideas remain at the edges of mainstream science, neither firmly established nor definitively refuted. The complexity of Earth's atmosphere makes it extraordinarily difficult to isolate causal relationships. Natural variability is so large that detecting external influences requires long time series and sophisticated statistical techniques. We may not know for decades whether the current conjunction of solar, magnetic, and atmospheric events is meaningful or merely coincidental. What we can say is that the atmosphere is demonstrating its capacity for extreme behavior. The same is true of the Sun. The same is true of the magnetic field. Across multiple Earth systems, we're observing conditions that fall outside the normal ranges of recent experience. This may be random variation. It may be the result of long-term trends that are only now becoming apparent. Or it may be a signal that we're entering a period of enhanced activity across multiple domains. The practical implications of the current cold event are immediate and concrete. Natural gas demand is spiking as heating systems work over time. Electricity grids are experiencing elevated loads. Roads are becoming hazardous as snow and ice accumulate. The homeless and the poorly housed face genuine danger from temperatures that can kill in hours without adequate protection. Emergency services are stretched thin responding to weather-related incidents. This is what the intersection of extreme events looks like in practice. Not dramatic disasters captured on camera, but the grinding accumulation of stresses on systems and people already operating near their limits. A geomagnetic storm knocks out a few radio signals. An Arctic blast strains the heating infrastructure. A transformer fails under the combined stress of cold weather electrical load and induced currents from the storm. The cascading consequences ripple through interconnected systems in ways that become visible only in retrospect. We are fortunate that the geomagnetic storm of the past 24 hours was relatively moderate, a G3 event rather than the G5 that a Carrington-class eruption would produce. We are fortunate that the cold, while extreme, is within the range that our infrastructure can handle. We are fortunate that the sunspot currently facing Earth has not yet produced its worst. But fortune is not a strategy, and the systems we depend upon were not designed for the confluence of extremes that is theoretically possible. Imagine a scenario in which a Carrington-class event coincides with an Arctic blast of the type we are experiencing. The geomagnetically induced currents damage transformers at precisely the moment when electrical demand is at its peak. The grid, already stressed by heating loads, experiences cascading failures. Millions of people in sub-zero temperatures lose power with no clear timeline for restoration. The consequences would be catastrophic in ways that few people have contemplated. This is not fear-mongering. It is risk assessment. The probability of such a confluence in any given week is extremely low. But the sun is active. The atmosphere is unstable. The magnetic field is evolving in unusual ways. The background level of risk is elevated, even if any specific extreme outcome remains unlikely. Those responsible for infrastructure resilience should be paying attention. And what about individuals? What can ordinary people do in the face of planetary-scale phenomena that seem entirely beyond personal control? The answer is both humbling and empowering. We cannot stop solar flares or polar vortex disruptions or geomagnetic jerks, but we can prepare for the consequences of extreme events. We can maintain supplies of food, water, and essential medications. We can have plans for heating and communication that do not depend on fragile infrastructure. We can build communities of mutual support that can function when normal services fail. This is not survivalism or paranoia. It is prudence. The same prudence that leads us to wear seatbelts and install smoke detectors should lead us to prepare for disruptions that history tells us will eventually occur. The question is not whether extreme events will happen, but whether we will be ready when they do. As we move toward the conclusion of our exploration tonight, let us step back and consider what we have covered. The massive sunspot facing Earth, the filament poised to trigger, the G3 storm that exceeded predictions, the Carrington warning from history, the earthquake precursors in the ionosphere, the oscillating inner core, the geomagnetic jerks that may have marked a planetary transition, the racing magnetic pole, and now the Arctic blast-driving record cold across the United States. These are not separate stories. They are different views of the same underlying reality. A planet embedded in a solar system, subject to forces that operate on timescales from minutes to millennia, connected by relationships we are only beginning to map. We live on a dynamic world, not a static stage. Understanding that dynamism, preparing for its consequences, maintaining humility in the face of forces beyond our control, these are the tasks that our time demands. Preparing for what comes next. We have travelled far tonight. From the blazing surface of the sun to the frozen iron heart of Earth, from the flickering ionosphere to the churning outer core. We have examined phenomena that unfold in seconds and processes that evolve over millennia. We have confronted risks that most people never consider, and connections that mainstream science is only beginning to acknowledge. Now, as we approach the quiet hours of the night, let us gather together what we have learned and consider what it means for how we live. The Sunspot Complex, AR 42944-296 remains facing Earth. As of today, December 4th, 2025, it continues to produce M-class flares with regularity. The filament structure nearby shows ongoing signs of instability. The solar physicists watching every fluctuation in that region cannot tell us with certainty what will happen next. The Sun may produce a Carrington-class event before this formation rotates off the visible disk. It may produce nothing more than the moderate activity we have already seen. We are watching and waiting, as humans have always watched the sky, hoping that the forces above remain benevolent. The G3 geomagnetic storm of the past day demonstrated that our models remain imperfect. The predicted G2 became G3 when multiple solar wind structures arrived simultaneously. The northern lights danced across skies from Alaska to Pennsylvania. The ionosphere rippled with disturbance. Radio operators experienced the familiar frustration of degraded signals. And somewhere, systems we depend upon absorbed stresses they were never specifically designed to handle. The magnetic pole continues its journey toward Siberia. The inner core continues its slow oscillation, currently in what may be a subrotating phase. The secular variation of the field continues to evolve along trajectories we can measure but not fully explain. Whether these changes presage something larger, an excursion, a reversal, or merely fluctuation within normal bounds, remains beyond our ability to predict. The Arctic blast gripping North America reminds us that the atmosphere, too, is capable of extremes that strain our infrastructure and endanger our people. The polar vortex is fractured, and the cold is here. It will persist for days, perhaps weeks. It will set records. It will force us to adapt to conditions we thought we'd conquered through technology and comfort. What does all of this mean for you, listening to these words in whatever corner of the world you call home? First, it means that you live on a planet that is not finished changing. The stable Earth of textbooks, with its fixed continents and reliable seasons and predictable magnetic field, is an abstraction. The real Earth is dynamic, evolving, subject to sudden shifts that can reshape the conditions of life with little warning. Our ancestors understood this intuitively, living as they did at the mercy of forces they could observe but not control. We have built a civilization that creates the illusion of control, but the illusion is fragile. Second, it means that preparation is not paranoia. Having supplies of food and water, having alternative means of heating and lighting, having plans for communication that do not depend on the electrical grid, these are not the obsessions of doomsday preppers. They are the prudent precautions of people who understand that complex systems fail, sometimes for reasons that could not have been predicted, sometimes for reasons that were warned about for decades before anyone listened. Third, it means that connection matters. When systems fail, communities survive. The bonds between neighbours, the networks of mutual aid, the relationships that transcend commercial transaction, these are the true infrastructure of resilience. No amount of stockpiled supplies can substitute for people who will help you when you need it, and whom you will help in return. Fourth, it means that awareness is valuable. Simply knowing that these phenomena exist, that the sun can disrupt our technology, that the magnetic field is changing, that the atmosphere can deliver extremes. This knowledge provides a framework for interpreting events that might otherwise seem random or incomprehensible. When the lights go out or the temperature plunges or strange lights appear in the sky, understanding what is happening reduces fear and enables rational response. Finally, it means that we are part of something vast and ancient. The processes we have discussed tonight began before life existed on Earth and will continue long after our species is gone. The sun has been erupting for billions of years. The core has been spinning since Earth's formation. The magnetic field has reversed hundreds of times. We are guests in a cosmos that did not create us and will not mourn our passing. There is strange comfort in this perspective. Our individual troubles shrink against such immensity. Our collective challenges become opportunities to demonstrate what we are capable of when we work together. I want to thank you for staying with me through this journey. We have covered ground that few programs attempt, weaving together solar physics and seismology, geomagnetism and atmospheric science, established facts and informed speculation. If I have erred in places, I trust you will investigate for yourself and reach your own conclusions. The goal is not to convince you of any particular worldview, but to expand your awareness of the systems that shape our existence. The world outside your window is larger than it appears. The sun is not just the source of light and warmth, but a nuclear furnace whose tantrums can reach across 100 million miles to shake our technology. The ground beneath your feet is not just solid rock, but a thin crust floating on currents of molten stone, itself floating on currents of liquid iron, themselves influenced by a solid inner core that is subtly, slowly, constantly moving. The air you breathe is part of an atmospheric engine that extends from the surface to the edge of space, connected to the magnetosphere, connected to the sun, connected to the galaxy beyond. You're embedded in this cosmic machinery. So is everyone you love. So is everything our species has built. Understanding that embedding is not a distraction from the practical business of life. It is the context that gives that business meaning. As you drift towards sleep tonight, perhaps you will look out your window. If the sky is clear and you are far enough north, you might see the aurora, the visible signature of processes we discussed hours ago. If the sky is clouded or your latitude too low, you might simply see stars, ancient light from suns that may themselves be erupting at this very moment, their flares racing through space toward planets we will never see. The universe is active. It is always active. And we are here on this small world trying to make sense of it all. Thank you for your attention. Thank you for your curiosity. Thank you for joining me on this exploration of the forces that shape our world. If you found value in what you heard, please take a moment to like this video and subscribe to the channel. Share it with someone who might appreciate a different perspective on the world we inhabit. Until next time, keep your eyes open and your mind curious. The show never stops. The sun keeps burning. The earth keeps spinning. The magnetic field keeps shifting. And we keep watching, trying to understand, preparing as best we can for whatever comes next. Rest well, my friend. Tomorrow brings new data, new observations, new mysteries to explore. The sunspot will still be there when you wake. The pole will still be drifting. The core will still be oscillating. And you will still be part of this extraordinary, terrifying, beautiful planetary system that we are privileged to call home. Good night. The information presented in this video represents the current scientific understanding combined with speculation about connections that remain under investigation. Nothing in this presentation should be construed as prediction of specific events or as advice for any particular course of action. The universe is under no obligation to conform to our models, and surprises are always possible. Stay curious, stay skeptical, stay prepared.